Hello friends, welcome to Abaqus Acumen for quick and sound learning. In this video tutorial, I will take you through how to plot the bending stress across the thickness of this composite shell plate. So this plate is made up of top layer aluminum and the bottom layer as a steel. We are defined through the composite cell section, and one of the takeaway would be to how to plot this kind of through thickness bending stress plot. The if you imagine the plate subjected to center bending or center loading, so it will be under a bending load, and due to this the top layer in a compression bending stress and the bottom layer would be in a tensile bending stress. So as this is a dissimilar material with a different modulus of elasticity and as well as the different thicknesses, the bending stress plot will be not linear. It started somewhere at the compression level at the aluminum top layer would be around 125 in compression MPa, that is 125 MPa in compression, and then followed by the up to this 1 millimeter thickness where the aluminum layer ends, and then again at this point the steel layer picks up with the compressive stress of 150 MPa, and then followed by the linear variation or transition from compression to tensile stress. Between it will have a neutral axis. The neutral axis transition is somewhere at this point, somewhere 1.4 millimeter, or sorry 1.6 or 7 millimeter. So this is how, once we go through this exercise, so we'll be learning how to plot this bending stress plot in Abaqus CAE. To do this tutorial, we'll start with geometry and we'll apply the loads bounding condition. So all this setup we'll do it in Abaqus CAE 6.12 simulation software. Just to give you some background about the physics of the problem, so we will take this simply supported plate with 70 millimeter width and 1 millimeter aluminum and then 2 millimeter as a steel, and you can imagine these are perfectly bonded, and then ultimately we'll be looking interested to plot this or know this bending stress contour across the thickness. As I explained, this start with the compressive stress, and then there will be a step in between where the steel material will be subject to compressive stress, and then there is a transition and there will be a neutral axis in between, and then there is a tensile bending stress. To get this kind of bending stress plot, it is critical from the CAE point of view to define the through section integration points. So in this example for the shell element, there are 5 integration point has been defined. Start with for at the top, or let's say bottom of the shell it is 1, and then at the top of the shell is 5. So this so for this we need to make a special request in output so that we can have the result or the stress values for each of these section points, and ultimately we should be able to get this kind of a plot. Guys, let's start with building the FE model for this 3-point bend of the shell plate. I'm going to start with a blank canvas. So this is a part. So quickly we'll build this geometry. This is deformable shell extrusion. Continue. So I'm going with 70 millimeter as a width of this plate. So this is, so it's 300 millimeter span. This is done. We'll go to property. So this is very regularly we create this material properties, that is aluminum, elastic. This is 68,000 MPa, 0.32. Say OK. So we'll create one more property, that is steel. .1 e raised to 5. So this is very familiar numbers for us. Dismiss, and then we create a section over here. So shell composite, so you have to choose a composite as a type, and you can put some name, section composite, something like that. shell composite, continue. So this is the first layer, that is aluminum, thickness is 1 millimeter, and orientation set to 0. Ply name is say aluminum, and that is your choice what ply name you can give. And second layer is a steel, the thickness is 2 millimeter, and orientation is 0. And then here you can put steel. Alright, so we are done with the property creation. So now we'll assign it. So this is, we choose this geometry. It's done. So we are done with assigning the property to this part. Let's do some partition of this shell plate, so that it will be convenient for us to apply boundary conditions, that is simply supported boundary conditions and the center boundary condition. To do that, I will go back to part and I will choose the partition with face. Okay, and you just select on any of this face, so it will go you to this grid canvas. Here I will do a partition exercise. Just observe. So these are the lines for applying the simply supported boundary condition at the edges, and then this is at center, and just I'm splitting it and creating it's done. Alright, so this is created. Now we'll create another part, that is roller part. Rigid roll. So this is discrete rigid shell extrusion, continue, and I choose circle. So the size of this roller is, that is 40 millimeter diameter, and so I will just modify the radius would be okay. So I have modified this dimension to 20 millimeter as a radius, so in diameter is 40. Done. So we're ready to extrude it. It's 70 millimeter, that is a width of the plate. Alright, so now we'll do a positioning of this plate. For that, you go to assembly, plate, select these two, just say OK. So we have to rotate this instance by 90 degree. There's a roller. Y is say 2 millimeter. Done. So 90, I will say minus 90. Alright, so we have flipped this. Now we have to position this. So for that, we will translate this instance. So translate this instance in Z direction by 150 millimeter to bring it at center. Okay, and then again, so just measure some distances to position it accurately. 30 millimeter in X direction. So again in Y direction. It's 20 millimeter. Alright, it is appropriately positioned. Now we'll send one or step creations. Go to step, create. So this is implicit static simulation in Abaqus, so you have to just say this is implicit static general. Continue with this, and here I am going with initial increment, that is load increment factor, that is 0.001. so this is a preferred value, or you can reduce it or increase it, depends upon how your simulation conditions are, inputs are. So here I start with 0.001. So this is the factor with which it will be applied with the with the load you are going to define in terms of displacement or force. So in this case we are defining the displacement of 4 millimeter for this rigid roller. So that 4 millimeter will be multiplied with this factor, and that particular displacement, this square meter displacement, is applied to this roller. Okay, dismiss. So I'll go to load, name is simply supported. So choose these lines. So use shift key. So we'll apply simply supported bonding condition y20. Now this is at center point BC. Continue. We'll be choosing center point. Done. So here we'll be applying the lateral conditions for stability. That is lateral displacements we have restricted at the center point. Now we'll we need to apply boundary conditions for the rigid roller as well. For that we need to create a reference point for this rigid roller. So go to part, and here we have to define reference point. So this should be fine. So this is your reference point for the rigid roller. So through this reference point we'll apply boundary conditions. So again go back to load module, and this is name it as RP reference point BC constraint. So and this is on the back side, that's fine. So we are restricting all the degrees of freedom except the y2. Continue with the same. Now we are applying a prescribed displacement to this part. So to select the same reference point. It's done. So will be y2 is now minus 4 millimeter. Okay, this is done. So now we'll go and mesh these parts. So I start with the plate part. So I'm okay with the 4 millimeter size. Let's say yes. So mesh is ready. And similarly for rigid roller, yeah guys, here I am going to keep some fine mesh for this rigid roller. For that I'm going with 2.5 millimeter. 2.4 should be fine. Just say done. Yes, this is ready. Mesh is ready. So now we'll define the interaction between these two parts. Where we are defining the contact definition through this interaction module. For that you go here and create. This is surface to surface contact. Okay, so continue. And master surface, so in general master surface is the stiffer one, and as this is a rigid roller, so it is a infinitely stiff body. So just recreate that. Sorry, continue. So this is my master surface. Done. And the color I'll be choosing brown, so which is outer skin. And now the slave type is again surface, and select these bottom surfaces, use the shift button, done. And here I'll be choosing the purple, which is facing towards the roller, purple. This is done. And I'll be defining friction, just a friction, mechanical, tangential waiver, penalty 0.4 should be suitable value for this application. Say OK, say done, dismiss. And there is one more critical step is left, so we need to define the output request for the integration point for this composite cell. So for that you go here and say create. This should be fine. Say continue, go with the pre-selected defaults, and here I am going to specify the integration points. Okay, that is 1, 2, 3, 4. This is for the aluminum, and then followed by the steel layer. So once we post process with the result, so Abaqus will give us the result for all these integration points, so that with these values only we could able to find the through thickness bending stress. So this is very important. So just say OK. And if you define a 5 integration points for each of the layer, then you have to go ahead and define all those integration points if you are interested to see the more detailed profile. Let's submit this run. So leave it to defaults. Just I'm looking at the status file. So guys, looks like there is some convergence issue in this model, so we are going to fix it. So for that we need to study the message file. So message file, I'm just looking at it, so understand what is the issue. Let me see what is the error. Okay, so here it is showing the system matrix has one negative eigenvalue. So this indicates that due to the negative eigenvalue, there are possibility of a rigid body motion of the any of this part, or of course the plate part. Plate is the one which is making this issue. So what I'm going to do is I'm going to fix this boundary condition, that is simply supported boundary condition, or I will say modify the boundary conditions from with additional rotational degree of freedom constraint. So I'm going to constrain this simply supported condition in rotational degree of freedom as well, that is degree due of 5 and 6. That's it. So we are restricting the rotation of this plate. It should resolve the issue of negative eigenvalue, and I will resubmit this job. Say I will put some name, say job 77, continue, just leave it to defaults again, submit. Okay, this new job, that is a status file, shows that the contact has been established and it is converging. So let's wait and see how it, so looks like it is smooth. So guys, you can see this simulation has completed, the analysis has completed successfully. So now I will load the result. So here it is. You can just animate this as well, you can just animate, and you can look at we will be interested to see the bending stress across this thickness of the dissimilar plate, that is aluminum and the steel layer. So for that what we can do is we go to XY data, say thickness, okay, and here you select the element nodal, and in element nodal you select S22, and select the element So I will try to select the center element. That is done. So we'll plot this. So this is for 4 nodes it has plotted. So I will just open one of the node, that is S22. Okay, and just change the fonts so that we can visualize it properly. And similarly over here. So guys, so this is what the bending stress plot across the thickness at aluminum layer. So it is in compressive load, that is a compressive bending stress. Here it is somewhere around minus 180 MPa as a value, bending stress value, and there will be a linear transition up to this point, and at this point there is a the end of the aluminum layer, and there is a step change in bending stress value for the steel due to the change in the modulus. So the resistance goes up and the stress, corresponding stresses, goes high, and it reaches up to somewhere around 220 MPa in a negative, that is a compression mode, and there is a linear transition from compression to tension bending stress, and there is somewhere the neutral axis is in this place. So this is how we have to interpret the bending stress results through thickness results. So guys, you can also plot the stress versus force versus displacement diagram. So for that you go to field output and unique node and select the force value, magnitude, and the displacement. Sets. So this is you have to do it for the reference node. So this is the value, and so I will do a cross plot for this. I hope you enjoyed watching this tutorial and found this informative, very informative. Please go ahead and like us if you find this video useful. Please go ahead and like us and subscribe our channel.